So in this lecture, we'll be looking at the concept of stochastic gradient descent, batch gradient descent, and mini batch gradient descent. In previous video, we looked at how we can train our neural networks using backpropagation and simple gradient descent. And this lecture will be diving much more deeper into the concept of gradient descent. Just a quick recap of how gradient descent works. We initially start with some random weights. We calculate the cost function as a function of our random weights, and then we calculate the gradient of our cost function with respect to w. So this is the gradient that we calculate, and then we update our weights using the gradient. So we update our weights in the direction opposite to the gradient with some learning rate alpha, and we keep on looping, we keep iterating this particular steps until we get the most optimal weights w where the cost function is minimum. So this was the simple concept of gradient descent. Let us look in much more detail what we were doing while doing the gradient descent. So we were looking at the idea of batch gradient descent. So let me explain what is batch gradient descent. So let's say we do have predictions and we do have actual values. So these predictions are done by the neural network. We do have n data points or n data examples up to 1 to n. What we can do is that we can calculate the loss for each of our data points. So for data point 1, the loss will be L1. For data point 2, the loss will be L2. For data point n, the loss will be Ln. And our cost function is nothing else but it is the mean of the loss that we have calculated. So it is the mean of the loss across the whole data set up to L1 to Ln. Once we have calculated our cost function, we can calculate the gradient of our cost function with respect to weights, and then we can update our weights accordingly. So this is the batch gradient descent. Why we are saying it as a batch gradient descent? Because we are calculating the cost function on the whole data set, that is on the whole batch. Okay. There are certain challenges with batch gradient descent. The most biggest challenge is computational challenge. So what happens over here is that if you want to calculate the cost function on the whole data set, you need to keep the whole data set into the memory. So let's say if you are having 10,000 training examples, you need to keep all those 10,000 training examples into the RAM. And if you are having a RAM of very small size, then it will be a problem. That's why this batch gradient descent is always not the most optimal option for training our neural networks. Okay, so here when we were calculating the cost function and we were updating our weights, so this whole step of calculating the cost function by taking the mean and then updating the weights, this is called as the one complete epoch. So in the current scenario of batch gradient descent, in a single epoch we are just doing a single iteration, but later on we'll be seeing in stochastic gradient descent and in mini batch gradient descent, a single epoch will be having multiple iterations. So let us start with an example of stochastic gradient descent. So in a stochastic gradient descent, what we'll be doing is that, let's say we do have again predictions and actual values. We'll be looking at the first training example. So in first training example, we'll be calculating the loss for this first training example using the prediction and the actual value. So this loss will be L1. Now for the first iteration of our stochastic gradient descent, this loss L1 will be our cost function. So J1 is nothing else but L1, which is where L1 is the loss for the first training example. Now we'll be calculating the gradient of this cost function J1 with respect to our weights, and we'll be updating our weights accordingly. So this whole process of calculating the cost function, updating our weights using this cost function J1 is the first iteration in our training. In second iteration, we'll be calculating our cost function will be loss L2. We'll be calculating the gradient of our cost function J2 with respect to W, and then again we'll be updating our weights. So in first step, we did updated our weights using the cost function J1. In second step, we are updating our weights using the cost function J2. In ith iteration, so if you are on the ith training example, that will be the ith iteration, our cost function Ji will be equals to Li, and again we'll be updating our weights with the gradient of the cost function Ji. So in a single epoch of stochastic gradient descent, we'll be performing the n iterations. So we'll be starting from first iteration where our cost function is j1, in second iteration our cost function is j2, and in nth iteration our cost function will be jn. So in each step we'll be calculating the cost function, then respective gradients, and then we'll be updating our weights accordingly. But again, this stochastic gradient descent is better as in comparison to the batch gradient descent because it is computationally less expensive, because we'll be storing just a single training example at a particular iteration. But the gradients that we calculate in stochastic gradient descent are very noisy. They are not in the direction of true gradients. So this is one major challenge with stochastic gradient descent. I'll be explaining it much more nicely in the last of this video using a diagram. Now coming to an example of mini batch gradient descent. So let us start with an example of batch size 4. So with batch size 4, what we are doing is that in first iteration, we'll be calculating the loss L1 from example 1, L2 from training example 2, L3 from training example 3, and L4 from training example 4. And from L1, L2, L3 and L4, we can calculate the cost function J1, J2, J3 and J4, and then correspondingly we can calculate the gradients del J1 by del W, del J2 by del W, del J3 by del W, and so on. Since we have considered the batch size of 4, we are just considering the first 4 cost function and hence first 4 gradients only. Okay. Now we can take the mean of this gradients that we have calculated. So we'll be taking the mean of first 4 gradients. So that will be the del J by del W. So this is the mean over here. And then we'll be updating our weights using the gradient, the mean of the gradient that we have calculated over here. So this is how we'll be updating our weights over here. So this whole step will complete our first iteration. In the ith iteration, we'll be taking the mean of gradient I plus 1, I plus 2, I plus 3 and I plus 4. And similarly, we'll be updating our weights over here. So in the first iteration, we took the examples from 1 to 4. In second iteration, we'll be taking the batch of 5, 6, 7, 8 and so on. In the ith iteration, we'll be considering the training example I plus 1, I plus 2, I plus 3 and I plus 4. So this is how our iterations will keep on going, and in single epoch we'll loop on the complete data set in the batches. So this will complete our single epoch over here. So this is an example of mini batch gradient descent. What are the advantages of using mini batch gradient descent? First of all, it is faster in computation as with respect to the batch gradient descent. It gives us the better estimate of true gradient. If you remember, in stochastic gradient descent, our gradients were very much noisy, but in mini batch gradient descent, our gradients will be much more better estimate of our true gradients. And because the convergence will be smoother over here, we can use large learning rates as well. In a stochastic gradient descent, we cannot use large learning rate because our gradients were noisy and we may get very much offset from the target of our weights. And since we can perform the updates of our neural network in the batches, we can parallelize our computation in case of mini batch gradient descent across the GPU. So these are certain advantages of using mini batch gradient descent. Now let us look at this with the help of an illustration or example. In batch gradient descent, we get the very accurate estimation of our gradients and hence will be converging towards our global minima very much faster, although it is computationally expensive. That's why we don't prefer to use batch gradient descent. In a stochastic gradient descent, you can see the gradients are very much noisy. They are not always pointing towards the global minima, but although with multiple iterations, you will definitely reach our global minima. In mini batch gradient descent, you can see that our gradients are much more in the direction of the true gradients. They are much more pointing towards our actual global minima, and because they are computationally less expensive, it is always better to use mini batch gradient descent. So this is all for this video. See you in the next video. Thank you.